So welcome back from the break, everybody. It's time for delving into condition monitoring and quality control. And the first presentation is provided by Konsta Sipilä from VTT on development of quality management tools for polymeric components. Welcome, Konsta.
Thank you, Monica, for the introduction. So, are the slides visible?
Yes, thank you.
Okay, great. So, the second topic today from my speeches is related to the development of quality management tools for polymeric components. We started this research 3 years ago, and we had a background that the plants were facing difficulties between different polymeric sealant sample batches, that the quality of different batches could vary quite a lot. So there was an idea or need for easy usable condition modeling techniques to verify the polymer quality between different sample batches. So that's why we initiated this study. So you probably all aware that the polymers are used in a wide range of applications inside nuclear power plants, cables and sealants due to their insulating and sealing properties. So composition of these commercially available polymers, they're not that standardized in detail as in case of metals. You have the very detailed information about the alloying elements that you have present in a certain metal alloy, but in the case of polymers, this is not so. So this may raise some issues if the manufacturers change the composition of the originally qualified or good material. And this may be due to the availability issues that the polymer provider or salesman faces. The subcontractor may have stopped producing some additive, or the use of additive may be restricted by legislation. So here we have the question then whether the changing of one component in the polymer composition, would that affect significantly the quality of the polymer? So to answer this, we should enlighten ourselves with more knowledge about polymer additives and how they are analyzed and how they affect the aging of these polymer components. So our plan, we developed this 4-stage plan, where in the first stage, we just obtain more information on additives and how they are analyzed. What are the analysis methods that you used in additive analysis? Then in the second stage, we identify those additives that contribute most significantly to the aging of polymers. And the third stage is that we identify the suitable analysis techniques that are also applicable for on-site purposes. And in the final stage, which I believe we currently have just started, is that we suggest practical analysis techniques for these on-site measurements. So generally these additives, they are added in the polymers during the manufacturing process. So polymers are typically manufactured from raw pellets, powder or resin, and extrusion or molding processes are involved here. So these raw materials, pellets, powders, and resins, they already may contain the additives, or if not, they can be added during the manufacturing phase using a separate mixing device or an extruder, as shown in here. Generally, the additives, they are dispersed into the major components, that is the polymer matrix in the molten state, either as dispersed phases, droplets, filaments, or agglomerates. And additives are used in polymers to improve the material properties. Firstly, they can be used to improve the processing properties of the melt during the manufacturing phase. secondly, they can improve the mechanical properties of the polymer, then chemical properties, then surface properties, and finally also visual appearance of the polymer. And there are a lot of different additives available. I was reading from one reference from year 95 that 13,000 different additives had been identified at that time, and the amount of additives has been increased significantly since. So there are many different types of additives available at the markets. I will go now a bit more detail through about what type of additives exactly are used. So the processing aids, as said, they are used to improve the processability of the melt. And this group of additives is the second most consumed additive group. Or in this processing aids, the most plasticizer is the secondly most used consumed additive group. And it's also identified that it has a function in the aging process, because plasticizers, they can diffuse from the material to the material surface and then evaporate away. So other processing aids that are used, I have listed basically them here. We have accelerators used speeding up the cross-linking of femsets. Then we have blowing agents, they used in the manufacture of foams. And then we have heat stabilizers, preventing degradation at elevated temperatures. Then lubricants, may have different types of functions. Then the plastifiers and generally processing aids improve the melt properties, and then release agents when are used to improve the detachments from the molds using manufacturing process. Then we have different additives used to improve the mechanical properties, and here again listed additives. We have compatibilizers, generally used to mix heterogeneous polymers that are immiscible to each other. Then we have fiber reinforcements, make the strength properties better. And then we have fillers, which is actually the largest group of additives produced. About 50% of the total volume of global additive markets, they are fillers. And these are particles typically less than 100 micrometer diameter that being conventionally used to decrease the cost of the manufacturing process. So you don't have to put up that much the actual polymer ingredient, which is more expensive, but nowadays they are also used for functional properties, let's say improving strength, stiffness, and so on. Then impact modifiers that improve the material's ability to absorb the impact energy. And then nucleating agents are used to affect the crystallization rate of the polymer. Then additives affecting the chemical properties, and here of this group or category, the most important one is the antioxidants. And here we have two different types of antioxidants. We have the primary antioxidants, which will interfere the direct oxidation reaction, and then the secondary antioxidants, which will prevent the oxidation caused by the oxidation products itself. And here we have a list of different types of other additives, biocides, kind growth regulation, cross-link agents affect directly the molecular structure of the polymer. Then we have flame retardants, photostabilizers, and also surfactants when emulsions are produced. Then additives affecting surface properties. This category is not necessarily that interesting in when you think about the applications in nuclear facilities, but here different kind of additives are used to change the surface properties. I think these additives are more relevant, let's say, in packing industries where we want to prevent, for example, sticking electrostatic forces. We want to prevent sticking of materials to each other. And then finally, we have the additives affecting the visual properties. So generally, the color additives are divided in two sections: dyes and pigments. They have slightly different functions in the polymer, and then also some polymer products consist also odorants, but not perhaps the industrial grade polymers in lesser extent. So from this listing of additives and going through literature related to the different additives, from the aging point of view, we concluded that the most interesting additives include antioxidants. This is quite obvious because they prevent oxidation of the polymer. Then we have fillers, especially when we have the relative amount of fillers versus the polymer. That can have a significant effect to the polymer quality. Then plasticizers, because they can evaporate from the material and thus significantly change the material properties. And then colorants that's which are related to the photostability of the material. So we concluded that if we are able to analyze these additives, we can also provide information on the quality of the polymer. Then we listed all the techniques that we could find that are used in additive analysis. So as you can see on the left-hand side, the list is rather long, and some of the interesting perspectives regarding these analysis methods are that they should be sophisticated enough that they are able to do qualitative and quantitative analysis, because you basically want to know how well your additive performs. So that kind of information is then required. Then one point of view that we thought is important: how much expertise you would require to operate this equipment, because some of these are quite high-tech equipment, so to say, and require quite a lot of training in order to use properly this equipment. Then the analysis should be fluent, so the sample preparation phase should be rather small. It shouldn't take too much time, especially when we think about doing analysis online. So it should be simple enough, the sample preparation phase. Then, of course, the equipment costs. Some of these are rather expensive equipment. It doesn't necessarily make sense to invest a large amount of money in these type of things. And then some of the analysis methods require a database on earlier analysis in order to function properly or get the most of the use of the measurement results. And then, of course, applicability for on-site measurements, the size of the equipment and other requirements for the equipment needs to be taken into account. And regarding these additives and analysis methods, we have prepared this VTT report. It should be available from the Energiforsk net website to be downloaded. Then we performed this kind of analysis, which methods would be the most suitable for online quality analysis of polymers. And the thing is that the analysis method should be fast and reliable, straightforward, so to say. So we had 3 criteria which we looked at each method. We wanted it to be sensitive enough, minimalistic sample preparations, and then what kind of other limitations the methods have. And we combined or summarized the data in this table form, and then we concluded that we would have 4 different analysis methods that would be potentially could be used at on-site analysis. So DSC, infrared, TGA, and XRD. And from these 4, we actually chose DSC and TGA. DSC for analysis of antioxidant and TGA analysis of filler amount for the next stage to kind of provide a proof of concept that whether these methods could be used at on-site. So analyze antioxidants with DSC. So the benefits of this method is a small sample size, about 10 milligrams. And it's basically inserted between 2 aluminum plates and put in the DSC chamber, which is heated up, let's say 200 degrees with a constant rate in nitrogen atmosphere. And the temperature is held constant, and the atmosphere changes from nitrogen to oxygen, and then the heat flow is recorded during this stage, and the major exothermic reaction that we can see from the data that is correlated to the oxidation of the base polymer. So when the oxidation of this base polymer starts, we can measure the time until that point, and we call that time as the oxidation induction time. So at this point, all of the antioxidants present in the material are consumed. So that's why we think this time would correlate with the antioxidant concentration, and obviously longer OIT times would indicate that there are more or better performance on antioxidants present in the material. Then the filler analysis, this is also a good method since it requires only a small amount of sample. Here we measure the mass of the sample as the sample is heated up. We have used 800 Celsius, but we can go even higher. And in principle is to evaporize every volatile species present in the material. So basically, what we have left is the filler material, which does not evaporate in these temperature ranges. And we can combine EDS, this analysis, and then analysis the remaining ash. What is the elemental composition of this ash, and yes, so on. So here, how we wanted to verify the resolution of these 2 methods, DSC and TGA. We discussed with James Walker, and they delivered us these special designed EPDM rubber samples where we have varied the antioxidant content and also the filler content, as you can see from the table. So the idea was that can these 2 methods, can they distinguish these samples from each other where we have the already known composition of antioxidants and fillers? And the next we will have first results on this exercise. So we completed the first round of measurements with DSC and TGA, and here in this left-hand side graph, you can see the OIT times as a function of the amount of. Actually, this is this should be amount of the antioxidant. But now I see that here is the wrong axis here. This is the filler particle. But anyways, the conclusion was here that you can see that when the antioxidant content is less than 1.2 pHr, you can see a decreasing trend. But then when the antioxidant amount is above 1.2 pHr, we really cannot distinguish difference between the samples. So it seems like this OIT would function with I don't know, maybe if I can say relatively low antioxidant contents, but when we have a relatively new fresh sample, at least based on these measurements, we didn't see any differences when the antioxidant content was high. And here on the right hand side, we just plotted all the curves, OIT curves that we had running. So there's it's clearly the process that we see after this 5 minutes or so when the polymer starts melting. Then regarding the TGA results, these were let's say interesting as well. We actually didn't see any differences between the filler content between the materials. And here again we should have a residual mass here, but for some reason the y-axis is different. But anywho, you can see from the figure the residual masses are not we couldn't distinguish the samples from each other, and we will. After this, we were wondering why this is. We looked a bit more detailed about the thermographs from the TGA, and they look very similar. Here we have two samples. The pink one is the sample with low amounts of fillers, and the blue curve here is the sample with higher filler amount. So basically the only difference that we see with these samples is in here the low temperature region, how it starts, how the material starts reacting here around let's say 400 degrees. So perhaps we should also look this part of the curve in more detail. Then we made some additional EDS analysis of the sample just to check what exactly is the composition of the remaining ash in the system. It was mostly carbon as we expected. We have small amounts of zinc and also oxygen, but I think this would be expected as already shown yesterday in Mohit's presentation. So in a summary, there are many additives that can be used to modify polymer properties. From the quality and the aging perspective, interesting additives include antioxidants, plasticizers, fillers, and some colorants. Several additive analysis methods are available, but many of those are quite laborious, require sample preparation, and have a limited on-site applicability. We have identified DSC and TGA from these methods listed as a potential on-site analysis methods to analyze antioxidant and filler contents. And results indicate that DSC, we could distinguish differences when in antioxidant content when the antioxidant content was less than 1.2 pHr. But we will still continue with this. We have been discussing with further optimization of the analysis process and so on. So we will continue working with this next year. Based on the TGI results, we did not, or the residual mass did not correlate with the filler content as we were kind of expecting. So we need to further analyze the thermographs. For example, whether we could use this method in filler analysis. This was my last slide. If you have any questions, please go ahead.
Thank you very much, Konsta. It's a very educational presentation, I think, a fantastic overview. But I do get a bit exhausted when I heard the number 13,000. How are we going to get sort of a grip of this?
Exactly.
So do you know of any like trends that you see from the manufacturer side that they start using some special kind of materials that they haven't used before, or?
I think that's the market is kind of living, and there are several things that are affecting. For example, the REACH legislation or system that will always find chemicals that are not they have some healthy or environmental hazards. So that's one thing affecting to the additive market, and of course then just simply if the polymer manufacturers don't have if the subcontractor just announces that they are not producing anymore some additives, so that causes also changes. So that's I think it is quite complex thing, the whole additive manufacturing business. So
yeah,
many things
yeah, definitely. Are there any questions from you guys to Konsta? Just raise your hand if you have a question. Mohit, please.
Yeah, just a short question, Konsta. No, it's not a question, but again, it's information. You have obtained this different antioxidant percents in the EPDM from James Walker.
Yeah.
Do you think, does it make sense if I test it in a microcalorimeter next year and try to see that if some change or some difference can be seen? And actually the thing is that I can also run a microcalorimeter like a DSC, but at slow scanning rate, so the entire material will be homogeneously like heated and a bigger sample mass, so probably.
Yeah, and I actually, when I was watching your presentation yesterday, some kind of comparison generally between DSC and microcalorimetry would be interesting to do.
Would you please send me this? Like, do you have some?
Yeah, we have this material, and I think you also need a really small sample. Maybe we can have a talk and discuss more detail what to do.
I appreciate that. Yeah.
Great. Thank you, Mohit. And Anneli?
It was not a question. I just wanted to say that I think it was very good and interesting presentation.
Thank you, Anneli.
Thank you.
Sanolo?
I did miss part of the presentation due to my colleagues running in and out, but you talked about additives and you have coloring, for example, and we have had some problem with different types of colors that make the same cable could have different properties if you have a green wire or red wire or a blue wire and so on. That's something that it could be quite big difference due to what color you use, and sometimes the color, if you take carbon black, for example, that is a protection from ultraviolet light, for example. And I did miss if you had that also, that you have a combination that some additives are in more than one table.
Yeah, well, not much on colorants in this presentation, but general overview. Some of the colorants act also as photo stabilizers, so they kind of protect the polymer from the UV aging. And also, I remember discussing with Sue Burnett on this topic as well. And if I remember correctly, she said that they may have also a role in the oxidation of the polymer, some of the colorants. So they may have an effect to the aging of the polymer. Yes, definitely.
Thank you, Sven-Olof. And you know what? You will be able to watch Konsta's entire presentation on YouTube afterwards. You can just lock the door and not let any colleagues in.
The weekend is saved.
Great. Then we have a question from Karin, and after that, a final question from Mauri, because then we have to move on to the next presentation. Karin.
Yes, I'm just wondering about the DEC and the OIT, because normally that's for polyolefins, and that what would the difference be if you have two different types of EPDMs? Because also that we know that two different types of hindered phenol stabilizers give different OITs even in the same material. So I'm just wondering, have you looked into that at all? And would you still think that technique, I don't think it's been used so much in elastomers.
Yeah, exactly. Yeah. So our perspective was that the polymers will or the antioxidants are consumed before we see the exothermal peak here. So it would affect the position of this peak in this graph. So we thought that more you have antioxidants, the more the peak would shift in this direction.
So it's not really an OIT, it's a different, or what's?
It's basically is OIT, because we define the OIT in starting point when this peak starts from here. But regarding the polyolefins you asked, I think I should discuss this with my colleague Harri Joki, who actually performed this measurement. So he would be a better person to answer this this question.
No, it's just also that there can be clear difference between different type of hindered phenols. One can give a much longer OIT, even if the real stabilization is not better. So like you've done here, to compare the same stabilizer in the same material, then you can, maybe in this case it looks like, it might not be super sensitive, but then you can use it. But to compare different materials with each other, now I can assume that even two different EPDMs would be difficult to compare with each other. So just I'm just curious to see how much you've done on this and on elastomers and EPDM in general, because I don't think there's so much in the literature.
Yeah, that's a good remark. Yeah, thanks.
Okay, thank you, Karin. And Mauri, the final question is from you.
Well, I just want to add some of this, Sven-Olof, what he's talking about, the colors. We have some experience from Forsmark about replacing some instrumental cables with the different colors, and probably we can share some information about that one. I'm not quite sure that we have any samples left, but we have reports written anyway.
Okay, so it would be really interesting to see those reports. Yeah.
Yes.
So I will connect you two. Thank you very much, Mauri.
Thank you.
And then it's time for the final presentation for the conference this year, and it's provided by Simone Suraci from University of Bologna.
Hello, everybody.
Hi, how are you?
I'm fine, thank you. So I share my screen.
Yes, please.
So okay, I guess that you can see my screen now.
Yes.
Okay.
Now it's in slideshow mode. Thank you.
Okay. Good morning, everybody. I'm Simone Suraci, postdoctoral researcher from the Laboratory of Innovative Materials for Electrical Systems at the University of Bologna. My today's speech is about the dielectric spectroscopy technique for non-destructive cable condition monitoring, and I will talk about theory and application of this technique to the low voltage cables. This is the table of contents of my presentation. I will start with the importance of condition monitoring and the characteristics of the ideal condition monitoring technique. Then I will move on with the operation principle of dielectric spectroscopy and how the additives and aging can impact the dielectric spectra after a brief recalling of the aging mechanisms. Then I will conclude with the correlation of the dielectric spectroscopy measurement with other state-of-art techniques, such as elongation at break. And then I will describe how to perform the dielectric spectroscopy measurements on site. So, starting from the condition monitoring, we have already talked about it quite spreadly during this conference. Anyway, as you know, the condition monitoring can be described as the assessment of the current state and the estimation of the future state of the system through measurements and calculation. It is very important because can bring to the can lead to corrective actions and maintenance that can be related not only to the time passed, but to particular events that can happen to the cable system, for example. I will also describe, maybe I put the pointer, sorry. Okay. I will describe the importance of condition monitoring through the graph you can see in the right-hand side of the slide, which relates the number of failures of the system and the cost of the actions, both preventive and repairing actions. This graph is divided into 3 sections. The first one is the preventive maintenance, when we have very low values, low number of failures, and we are increasing the cost of actions because we are doing more prevention actions there than needed. Obviously, since the number of failures are very low, also the cost of these repair actions are very low. Then on the far right, we have the reactive maintenance, and it happens when the number of failures are very high inside the system. So we need to take repair actions, which can be very, very costly. In the middle between these two parts, there's the condition monitoring, where we balance both the repair action and the prevention actions, and we can have the minimum of cost since we are, again, doing repair and prevention actions depending on the current state of the system. However, not all the condition monitoring techniques are good to be used for evaluate the state of the system. In particular, the condition monitoring techniques should be associated to properties that obviously must be related with the system aging, that should have a monotonic variation of the property with time, and in particular, they should not have a abrupt variation of the property throughout the aging, for example, year and year. While in the right-hand side of the slide, you can see some of the characteristics of an ideal condition monitoring technique. For example, it has to be non-destructive. There should be a universal acceptance criterion for the maintenance. It should be easily replicable with low error dispersion, and it should be referred to the bulk of the insulation. As you know, up to now, the state of art for condition monitoring inside cables is the elongation at break. Here you can see the table, some pros and cons of this technique. Obviously, the pros are the fact that this method has been used over many years. It has very good correlation with polymer degradation level, and it guarantees also minimum bending properties of the cables. But on the other side, it is strictly related to the local defects, so it is not referred to the bulk of the insulation, but just to a particular piece of cable. It can be affected by huge error displacement. We have already seen some results during these days. And in particular, it does not consider different polymeric materials, such as we have no differences of the elongation at break end-of-life criterion between rubbers and, for example, semi-crystalline polymers. In the lower part of the slide, you can see the pros and cons of the dielectric spectroscopy technique. As I was saying, it is a not destructive technique. We will see that, but it has very good correlation with polymer degradation level. It usually has a lower dispersion, it is referred to the bulk of the insulation, and it is performable in situ. As a con, we have the fact that we are not able to localize the aged spots, and up to now there's no universal acceptance criterion which is strictly defined. So this being said, let's move on to the operation principle. The operation principle at the basis of the dielectric spectroscopy technique is the polarization. The polarization is defined as the response of the insulating material, in the dielectric material, to an external applied electric field. This electric field can have different frequencies, and depending on the frequencies of the applied electric field, we can have 4 different polarization mechanisms. Here in the graph you can see the trend of the real and imaginary part of permittivity as a function of the applied frequencies. So the first polarization which occurs at very high frequencies, in this frequency region 10 to the 18th up to 10 to the 13 Hertz, is represented by the deformation of the electronic cloud around the atomic nuclei. While if we move to lower frequencies, we can move to the atomic polarization. In this case, we are not considering the atomic cloud, but we are considering the molecule. And with the atomic polarization, the electric field brings to the deformation of the molecules, as it can be seen, for example, in this image here. Further, the polarization mechanisms are the dipolar polarization and interfacial polarization. The dipolar polarization in particular is very important because it is related to materials with permanent dipoles. So, for example, polymers with oxidized chains, which exhibit permanent dipoles. The dipolar polarization is characterized by the fact that the electric field brings to the orientation of these dipoles in the direction of the electric field. Finally, we have the interfacial polarization, also called Maxwell-Wagner-Sillars polarization, which occurs at very low frequency, lower than 10 Hertz, for example, and it is related to the free charges which are displaced next to the interfaces. For example, if we are considering semi-crystalline polymers, we can have interfaces between amorphous and crystalline phase, or if we are considering different polymers, we can obviously have also interfaces between additives and main polymer matrix. This interfacial polarization is usually quite difficult to be analyzed because in the lowest frequency region we can also have the quasi-AC conduction. The quasi-AC conduction brings to the hiding of the imaginary part of permittivity trend due to the fact that the trend of the imaginary part of permittivity is led by the movement of charges, which brings to the so-called conduction. The quantity which measures the intensity of the polarization, I have briefly reported before, is the complex permittivity. The complex permittivity is made up of 2 different parts. We have the real part of permittivity, which is related to the energy stored inside the material, and then we have the imaginary part of permittivity, which is related to the dielectric losses. All the quantities obviously are function of the frequency, which is reported here as angular frequency omega. One quantity that probably you have heard about is the tangent delta, also called dissipation factor, which is directly related to the dielectric losses, so the complex permittivity actually. It also refers to the conductivity of the material. But at high frequency we can neglect this term because the omega values is very high, so all the first ratio can be neglected. It is the tangent delta can be also, can I say, drawn in a phase graph where we can have the fact that for perfect dielectrics we expect that the current is leading by an angle of 90 degrees with respect to the applied voltage. In a real condition, for real dielectrics, it does not occur, because we have this little angle here, that is the angular deviation from the 90 degrees, which is delta, whose tangent, the tangent delta, represents the dissipation factor. And it also is directly related to the energy dissipated by the dielectric system due to both polarization mechanisms and conduction losses, because we have the fact that insulating materials are not perfect insulating materials, so we have a non-infinite resistance. So before moving to the results coming by the application of this technique to, for example, cables, I will briefly recall the aging mechanisms. They have already described by Konsta today and yesterday by the researcher at PNNL. Anyway, just to recall that the aging stresses can bring to the macroscopical embrittlement of the material and the loss of ability in plastic deformation of polymers. This aging obviously is made up of different steps. We have the initial consumption and physical loss of the antioxidant. After the consumption of antioxidant, we have the inception of oxidation, which can be catalyzed by high temperature or radiation. And as a product of the oxidation process, we have the chain scission and the chemical crystallization, which brings finally to the embrittlement of the material. In this slide, you can see some graphs that have been already taken by, reported by Konsta today. In particular, they represent the chain reactions of the oxidation inside polyolefins. The only difference between these two graphs is the presence of the antioxidants. So without antioxidant, we have this chain here, while with antioxidant, we have this other chain here. What does have in common all these species have in common? They are polar species, and with these characteristics, they can respond electrically in the dipolar polarization area of the dielectric spectrum. And this is very important to evaluate the evolution of aging, because obviously, as we increase the concentration of polar species, so for example, we are increasing the concentration of ketones, carboxyl groups, hydroperoxides, we are also increasing the dipolar polarization. So the device used for the acquisition of the dielectric spectra is the Novocontrol Alpha dielectric analyzer that we have in the lab. It works with applied voltage of 3 volts in a wide range of temperature and in a frequency region between 10 to the -2 and 10 to the 6 Hertz. And as I presented before, this frequency region can be related to the dipolar interfacial polarization and also to the QDC conduction. It is evident that the frequency region to focus on is the higher frequency region, which is related to the dipolar polarization, which can be again related to oxidation products, both antioxidant degradation products and oxidized polymer chains. We will also discuss a little bit about the low frequency response in the following slides, but we can just conclude that if we have a high concentration of additives, the interfaces are very, very high, and we cannot see the contribution of oxidation products. These are the cable specimens that we have using in the Team Cables project that was already presented by Jukka yesterday. In this project, we have 2 different cable structures. We have a coaxial cable geometry and a twisted pair cable geometry with 2 different polymeric compounds, which are based on the same cross-linked polyethylene. It is a silane-based cross-linked polyethylene. We have the first compound, which is made up of polyethylene plus 2 different antioxidant, 1 primary antioxidant and 1 secondary antioxidant with concentration of 1 pHr each. And then we have the second compound where we have obviously the polyethylene matrix plus the 2 antioxidants plus 50 pHr of flame retardants, so ATH in this case. So we have a very high concentration of flame retardants. The first analysis that we have performed is obviously how the concentration of additives impact the dielectric spectrum. Here you can see the trend of the imaginary part of permittivity at high frequency as a function of the concentration of the primary antioxidant, secondary antioxidant, and ATH. As you can see, and as it is expected, as we increase the concentration of additives, so as we are increasing the concentration of the polar species, we are increasing the imaginary part of permittivity response, so the electrical response. It is true until we reach a threshold value, which also corresponds chemically to the maximum soluble additives inside the polymeric matrix. We have actually the chemical department has done some measurements to assess this value. Beyond this value, we have a stabilization of the property. This was expected again because at high concentration, these additives can agglomerate, in particular antioxidants can agglomerate into crystals, and we are now considering the interfaces of these species. So we are moving towards different frequency regions which are not related to the highest frequency region here reported. And it is also present, obviously, in the case of ATH due to the hydrogen bonds that can be created with high concentrations. But since we are considering this property, this technique as a condition monitoring technique, we have also investigated the response of the dielectric spectra with aging. Here there's some characteristics of the aging process, accelerated aging process we have performed inside the Team Cables project. We have 4 different aging conditions, 3 of them at room temperature with dose rate ranging from 8 grays per hour up to 400 grays per hour, and then a combined aging with low dose rate and higher temperature. These are the results coming from the coaxial cable for the 4 different aging conditions considered. In all the dielectric spectra you can see here, we have 2 different peaks, one in the highest frequency region, which is related to the dipolar polarization, and one in the lowest frequency region, which is related again to the interfacial polarization and QDC conduction phenomena. Focusing on the highest frequency region, you can see that during the first aging, so from the black line to the red line, we have a reduction of the dissipation factor values, so the dielectric losses. This was imputed to the consumption of the antioxidants, because inside this material we have a very high concentration of additives, which again brought to very high dielectric losses. But then after the initial consumption of the antioxidant, we have like a new baseline from which further aging brings to the increase of the dielectric losses for all the conditions considered. This was again imputed to the increase of new dipolar species in terms of concentrations, both due to the fact that we are introducing new antioxidant degradation products, and on the other side, we are also creating new oxidized species and radicals. For the low frequency dielectric response, you can see that we have no monotonic increase of the property. In some cases, the curves are, for example, overlapped, and it was again expected, because with aging we cannot single out the different interfaces coming from aging or the one coming from, for example, radical recombinations. So that the interfacial polarization is very difficult to be analyzed without further, for example, chemical analysis or SEM analysis. In this slide, you can see maybe a better view of the trend of the dissipation factor as a function of the aging time for the 3 different cables analyzed. So we have the coaxial cable, we have the twisted pair non-filled cable, which has the same polymeric compound as the coaxial cable, and then the twisted pair filled cable, which is made up of the polyethylene plus both antioxidants plus the ATH. As you can see here, if we plot the value of tangent delta at high frequency as a function of the aging time for the four different aging conditions considered, we have that the dielectric losses increase with aging. That is again already expected and already presented. But what is important is that as we increase the harshness of the aging conditions, we are also increasing the steepness of the dielectric losses increasing curve. For example, here it's more evident, and in particular we have that if we consider the combined aging, we have more or less the same trend, which is shifted upwards because of the contribution of temperature. This being said, we can conclude that the dielectric property at high frequency is suitable for to be used as an aging marker for cable aging evaluation. But to further confirm the suitability of this technique to follow aging, we have performed some correlations. In particular, we have performed correlations with the elongation break and the ester index from FTIR analysis. In particular, focusing on the elongation at break, we have for all the materials and for all the aging conditions considered, a unique master curve which corresponds to the reduction of elongation at break, which brings to the increase of the tangent delta values. What is important here is the fact that if we focus on the blue dots, which are related to the coaxial cable, and the red dots, which are related to the twisted pair non-filled twisted pair cable, so we have the same polymeric compound, we see that practically no impact of the cable structure can be seen. And in particular, we have like a unique cluster related to the materials without ATH. On the contrary, if we introduce ATH inside the cable insulation, we have that the cluster is shifted downwards with lower values of elongation at break, and this was again expected because we are introducing external inorganic species, which brings to an abrupt decay of the mechanical performance of the polymer. But we are also introducing polar species, so we are moving towards higher values of dissipation factor. So it is possible to define a unique master curve which perfectly correlates the elongation at break with the dissipation factor coming from the dielectric spectroscopy technique. Similar reasoning can be done for the ester index, and in particular it is very significant because it guarantees the fact that with dielectric spectroscopy we can follow the oxidation product concentrations. And again, we have, other than a very high scatters because of the fact that FTIR analysis are very localized analysis while we are considering the bulk of the material. Anyway, besides this, we can see a unique trend which correlates the increase of the ester index, so the increase of the oxidized species, with the tangent delta values at high frequencies. So, however, since we are considering the real cables, how we can apply this technique on site? Regarding the cable connections, for example, here you can see the cable specimens that we have used. We have put at cable terminations 2 plugs for the coaxial cable and the twisted pair cables, one connected to the inner conductor and the other one connected to the shielding, and the measurement is done between these two, let's say, electrodes. But we have also wanted to build a portable device which is able to perform the dielectric spectroscopy in the frequency region of interest, so the one that I have just described, so the highest frequency one. To do so, we have built a portable dielectric analyzer that is reported here in the picture. The setup is made up of a dielectric analyzer in which there are some acquisition cards, a signal generator which applies the voltage with different, obviously, frequency, and then a PC to acquire the data. It's a software, a LabVIEW software based on the acquisition card. The frequency region analyzed is between 1 and 200 kHz, and the applied voltage depends on the signal generator, but in our case is up to 10 volts. The first step after building the portable device was the validation of the portable device. In particular, we have validated the values coming from the portable device with a lab scale LCR meter. And as you can see, we have a perfect correspondence between the experimental values coming from LCR meter and the new portable device that we have built. Then we moved to the sensitivity analysis, and it was a very interesting work because the idea was to identify a threshold value beyond which we have appreciable variations of tangent delta. How we can obtain this damage ratio? We have aged cables with different lengths, and then we have cut the cables in different parts, so that we have cables with increasing aging length, starting from 0%, which represents the unaged cable. And then we moved up to 100%, so the cable which was totally aged. Obviously, the damage ratio is defined as the length of the aged part over the total cable length. And what we have seen is reported in this slide, and in particular, I will focus on the tangent delta trend. I don't know if it can be clear now, but the black line is referred to the unaged cable, and the pink one is referred to the total, the globally aged cable. In the middle, we have the different values of percentage of the damage ratios. What is interesting here is the fact that, first conclusion, we can evaluate the aging inside the cable, comparing the 0% up to the 100%. Then of aged ratio. Then another important conclusion is the fact that with the tangent delta values, we can follow the dilution and concentration of the aged sections. For example, we have that 50% of the aged sample, so it means that the cable is aged only in half of its total length, is perfectly in the middle of this range between 0 and 100%. For a better viewing of these results, I've reported also the values of tangent delta percentage variations as a function of the damage ratio for 3 different fixed frequencies. And as you can see, depending on the frequency considered, we have a monotonic increase of the property as we increase the concentration of aged parts. In particular, we have that at very low damage ratios, only 50 kHz is suitable for the evaluation of aging, but the variations are very low and can be related to the measurement setup. So it is preferred to consider bigger variations, so values higher than 30%. So, moving to the conclusions, we have seen that the radiochemical aging modifies the physical, chemical, and electrical properties of the polyethylene. we have seen that additives and in particular antioxidant can have an impact on aging. In particular, obviously, antioxidant can delay the oxidation chain to start. Then we have seen that the dielectric spectroscopy at high frequency follow the polymer changes caused by aging, suggesting the suitability of this technique for cable condition monitoring. And we have also correlated these the results with other properties such as mechanical and ester index. And finally, we have presented the portable device, which was again suitable for the aging evaluation on site. So this concludes my speech. Obviously, if there's any questions, they are very welcome.
Thank you very much, Simone. Are there any questions? I can start. I'm not really familiar with the sort of the dose that a cable normally receives in a nuclear power plant. Is it, if you look at the doses that you have used in your tests, is that like a conservative choice, that it's a higher dose than expected in the plant, or is this what the cables are facing?
Yeah, actually, they are very higher than the one that cables usually face inside the nuclear environments. It depends on, obviously, on the area inside the nuclear plant where these cables are placed. But usually the dose rates are very lower, also lower than the low dose rate. Anyway, due to the constraints in time, it is important to produce an accelerated aging. But the key is not to create the so-called diffusion limited oxidation, as it was presented by the PNL researcher yesterday. In particular, we have seen the chemical analysis showed that no DLO was present inside the materials analyzed. So I would say that this aging is obviously accelerated because of the very high doses, but it is not related to the DLO effect.
But still, you think that with the sort of the normal rates that the cables do face in the plants, the method will still be applicable, or?
Yeah, it's quite difficult to reply at this question, obviously, because we have seen that the aging time is more impacting than the dose rate, actually. Okay. So the ideal condition should be like having a very low dose rate, simulating the one in nuclear plants, but it means like up to 0.3 grays per hour, with very long aging times, like 40 years.
But if you would be able to compare maybe a stored cable with a cable that has been in service, would that be a good idea, or?
Yeah, sure. It is very difficult to find decommissioned cables, usually. Indeed, inside the project, we have new cables that have been aged. Unfortunately, we do not have cables that are actually decommissioned, so the ones that actually were in operation. I know that, for example, some operating companies have a sort of storage of cables, but it's very, I mean, we have never received some of them, so I know it's very difficult to obtain real cables, with long aging and the real condition aging condition.
Yeah, maybe especially to get both a stored cable that has been stored sort of in the right way, and then a cable that has been in service, because I guess that cables that have been in service that should be able to get that from the decommissioned plants within a couple of years or so.
Yeah, that could be very interesting also for our kind of measurements, because they are non-destructive. So actually we can see the limits, how much is the variation in real conditions and not accelerated conditions. Yeah.
Thank you. And are there any other questions to Simone? Henrik Toss, please.
Hi, Simone. Very nice presentation. I was just wondering when you do the if you want to do the testing on site, how do you connect to the cables?
Yeah, as I was saying in this slide, from the cable terminations, it is possible to obtain both the conductor and the shielding. So the idea is to plug these BNC cables, which can be then plugged into the device. I mean, it is a non-destructive technique, so actually just unplug the cable from the equipment and plug to the device, to the portable device, should be enough. We have performed some measurements on site. In that case, cables were plugged through Type N connectors. So we have done some there are some connectors that adapt between Type N and BNC. So we have plugged directly on the device with this adapter.
Okay, so you can you have just an adapter that you made and you plug that in.
Yeah, it depends on the connector type. In that case, they were Type N connectors, and they are commercially available adapters. But usually, I mean, the idea at the base is just to have the conductor and the shielding separated. It is possible usually, and then the connection can be done also externally. I would not say with floating electrodes, but some other adapters can be used.
Do you need to calibrate to get rid of the effect of the adapter?
Yeah, usually yes. It can be